Next, we'll bind the WebSocket logic and MapUI to bring this all together. We can get started with a location service class, similarly to the user service class that would abstract the local location. Unlike the user service class, the location service class should also deal with the physical location of the device. These are the same constants we have on the server. When sending a location update to the server, I don't want to exceed a fixed amount of updates, so we won't burden the server or our network. The class has a private constructor, so the only way to create the location service is via the bind method, which in turn invokes the instance method bindImpl. We provide two callbacks. One is for a car being added, which we will use to bind a new car to the UI, and the other is for location updates, so we can position the map. Location update notifies the server about changes to the location, and also invokes the callback once we can position the map. We invoke the callback with the location, so the map can be shifted to our current position. Once the server socket is connected, we start sending location updates there. We open the WebSocket connection using the connect call. We cache the last set of values so we don't send data to the server unless something changed. EasyThreads lets us post jobs onto a dedicated thread, so we don't have to block the main EDT. It also means we don't need to deal with synchronization or any other complexity related to that, as all operations happen on that thread. Until onOpen is invoked, the connection isn't ready. That's why the server member field is only initialized here, when it's actually ready. If we already have a location, we should send a user location update once we have the socket connection in place. The connection is single-threaded, as I mentioned before. The isThisIt method is similar to isEDT and indicates if the current thread is the one managed by the EasyThread. If not, we use the runnable, which invokes the target runnable on the EasyThread, similarly to call serially. If the values didn't change since last update, so we do nothing. We don't update too much. There is a chance we'll miss an update here, but it's probably not a deal breaker if a user didn't move much. We create a byte array output stream into which we construct the message that we received on the server with the header, location, etc. I currently hard-coded a 1 kilometer search radius and defined explicitly that we aren't in taxi hailing mode. One line to actually send the binary data. It would be similar with text data with the exception of passing overhead. The IO exception isn't likely, as this is a RAM-based stream. Here we received the messages sent from the server, specifically driver search result. We store user instances in a map where the user ID is the key. This saves us from sending duplicate car added events and allows us to just mutate the user properties, which other code can observe using the built-in listeners in properties. Notice that this code is running on the WebSocket thread, so events need to go back into the EDT to prevent potential issues. This is really important. We need to handle errors properly in a WebSocket application, otherwise a failure can leave us without a connection. The callback interface is trivial. It's mostly used as a Lambda expression in the code. And that's it for the location service.